So everyone, I'm going to start early with the background on Stacy because she has a very distinguished background, and I want to make sure everyone understands what a great speaker and quality person that we have here today. So Stacy is a deep learning engineer at Weights and Biases, building developer tools for accessibility, transparency, and collaboration in deep learning. Her research in computer vision and natural language processing includes image aesthetic quality and style classification, object recognition, photo caption generation, and language modeling for emoji. She has worked extensively on image search, data pipelines, productization, machine learning systems, automating content discovery and recommendation on Flickr, the first and longest active photo sharing website. Prior to Flickr, she developed a visual similarity search engine with Lookflow, a startup of 5 engineers which Yahoo acquired in 2013. Stacy holds a Bachelor of Science and a Master's of Science in Symbolic Systems from Stanford University. So I ask everyone to welcome Stacy, and Stacy, take it away.
Thank you. Hi, everyone. Thanks so much for the intro, Abe. Thanks so much for joining for this talk. I'm Stacy, and I'm a deep learning engineer at Weights and Biases, building developer tools for machine learning. I'm here to talk about how to tune deep learning models faster. I won't get much into the mathematical details of different algorithms or tell you the best hyperparameters for a given problem because the space is so vast and varies so much. Instead, I'll focus on high-level insights from reproducing and fine-tuning a bunch of models over the last 2 years. In my setup, I'm usually forking some code for an existing model from GitHub and instrumenting it with logging and visualizations. I'm trying to move as quickly as possible so I can showcase more diverse machine learning use cases on our platform, while also understanding enough about each model to say something interesting and helpful in my reports. I'll show lots of screenshots from Weights and Biases because that's where I track all my experiments, but the general approach should work in any developer environment and with any framework. If you haven't encountered the explore-exploit trade-off I mentioned in my title before, it's a useful handle for many life situations. It comes from the multi-armed bandit problem, where classically, you're in a casino and all the slot machines have a different, unknown, and probably really tiny probability of paying out money. So how do you maximize your winnings? Do you try a bunch of machines once, explore, or do you pick one and play it over and over, hoping that you picked a good one? This is exploit. And these two worlds do share some features in the hyperparameter tuning slot machine. It's hard to know if I'm really winning or what's really happening versus the story that I'm telling myself. So with the same series of events, if I just lost 20 times in a row, I might be thinking, I'm doing great, I'm having fun, or, oh, this is awful, and I'll never get this model accuracy above 65%. It's hard to stop. That's it. I can't lose any more money, and this is as good as this model can possibly get. It can be hard, but very useful to reflect on the experience, honestly. What did I get out of this process? What can I learn or do better next time? And if we're going to play a slot machine with known risks, it can help to be intentional and think about constraints. How much will I spend or how long will I play for? Regularly reflect on what's happening. So this is how much I've actually spent or how many runs I've actually launched, how much GPU compute I've used, and learn from experience. Next time I'll bring even less cash. So what is hyperparameter tuning? Hyperparameter tuning, or optimization, is the task of finding the best hyperparameters for a given learning algorithm, which for this talk is going to be a convolutional or recurrent neural network, as tuning GANs and reinforcement learning models could take its own talk, and often it's hard to express the quality of those with just an objective number. And this tuning can be done entirely by hand. Run one experiment, look at the results, change one hyperparameter, run the next experiment, and so on. But of course, this process is really slow, and we want to go meta on the manual practice. And there's lots of research about and different tools for this, both paid and open source, for the algorithmic or automated aspect. So if we need to try a bunch of different combinations anyways, how do we optimally pick the next best combination to try? and thereby run fewer experiments, waste fewer computing resources, and just get the results we want even faster. The most common methods for this are grid, random, and model-based optimization, likely Bayesian or Bayes, though you'll hear lots of other terms and strategies in this space. Fortunately, we know a bit more about the payouts of these strategies than of the slot machines. Grid search just tries all possible combinations exhaustively, which can be really useful if your search space is small and you want to guarantee finding the best option. Random search is generally faster and recommended if you have a larger search space because it will sample more around the search space and give you a sense of the various possibilities faster. But it is not guaranteed to find the best combination. Bayesian optimization tries to build a probabilistic model of the function going from your hyperparameters to a target measure of your performance. Usually that's accuracy on the validation set. So this Bayesian model of your actual model that you're training tries to predict what values to try next based on all of the values and the results it's seen so far. And this process actually tries to balance the explore-exploit trade-off by both trying values that it's still unsure about to learn more about the space, and also ones that it expects to be near optimal. In practice, Bayes works faster than grid and random because it runs fewer bad experiments. One caveat being is that it requires a target metric to optimize, which you might not always have. There's a long tail of other methods like gradient-based optimization, early stopping of unpromising runs, evolutionary optimization, and even population-based training. And there's a lot more options than I can cover in this talk, including black box optimization services for any model. At a high level, once you're looking into these details and different trade-offs, I would ask myself, am I at the stage where I've thought through the specific model I'm tuning and the specific problem that I'm solving? And is there nothing else clever that I can do for this specific problem, and I just want to throw GPUs at this and be done? If the answer is yes, then I'd suggest using some optimization, like Bayes, because it will generally work faster, and then go think about something else. But in my experience, the more interesting, challenging, and rewarding work of hyperparameter tuning happens before that stage. And we don't really have a good general algorithm for it yet, and that's why many of us still have jobs. So let's get to that part. So advancing the slides. Before you actually run any sort of hyperparameter sweep, you get to decide what hyperparameter even is. And there's an important distinction between the regular parameters of your network, like the model weights and biases, which are themselves learned or iteratively improved during the training process, and the hyperparameters, which are configured outside the training process and generally fixed for its duration, though some could be adaptive, like learning rate. For a given network, these can include the number of epochs, learning optimizer type, batch size, rate decay, and much more. The network architecture itself could be a hyperparameter, especially if you're starting from a well-known base network like Inception or ResNet. How many layers are you freezing or fine-tuning? You know, the number and type and size of all your layers, as well as the connection patterns and the dimensions of the sliding window. All of these can be hyperparameters. And as you decide whether to fix a certain hyperparameter and keep it constant in your code or vary it and explore it, you might think about how much you know about this hyperparameter in advance, and how will this hyperparameter affect the overall runtime and complexity of your search. Epochs is an easy one because it's well understood. When I'm running repeated experiments, I generally want to set this high enough to see definite improvement, but not so high that I'm wasting time on a very slowly converging curve. I usually go for about 10 epochs if I can get away with it, as long as I can see the loss decrease and start to asymptote. Seeing improvement in validation loss is especially important to make sure that I'm not just memorizing the training data. Dataset size is another well-known hyperparameter. Generally, if your data sample is representative of your problem and your split is unbiased, then the larger your data set, the better your performance. But of course, the longer each of your experiments takes to run. I usually follow the conventional wisdom of splitting your full data into 80% for training, 10% for validation, and 10% for test, which is a holdout that you don't even look at until you're done. And then as you train on the 80%, you validate on the 10% after every epoch. In practice, if I'm running a search or a sweep, I am actually lowering these to about 20 to 50% of each split. And that's convenient because I'm often testing the code on a very small subset of my data in practice anyways to make sure that it runs end to end, that the data loads correctly, and so forth. And I generally try to get the runtime of one experiment down to a few minutes if I can. Then after each set of experiments, or sweep, or hyperparameter search, you can test for the full data set, and hopefully the observed patterns will generally hold and maybe even give you a slight increase. If adding more data doesn't help or hurts, you might be overfitting and may need to increase the percentage you're using for each sweep. Validation data is especially tricky to fix here because the smaller sample that you're taking might not be representative and noisy. One solution here is to pick the validation set randomly each time, and just keep in mind that if anything, you're solving a harder problem. And remember to verify the robustness of your solution, that it works for the larger validation set also after you're done with the sweep. And this is a good framework for your process. I call it iterative sweeps, or repeated phases of tuning and then testing on the full training and validation sets. In each sweep, you decide, perhaps implicitly, which hyperparameters stay fixed in the code and which ones you will test by varying them. And so one of your first choices is how much to change at a time. If you run a sweep over every possible setting, or if you test too many values for a specific hyperparameter, then you'll need to wait a really long time for results. And of course, one thing that I've been glossing over here is that all of these factors are not independent. In a perfect world, we would love to see a clean interaction between every hyperparameter and the target metric, but that's not how they operate. This is an example of the cleanest parameter interaction or parallel coordinates plot that I've ever logged. And I definitely want to dig into the subtleties here because I'm skeptical of this conclusion. But basically, each line here is one of 139 countries. And the economic indicators like production and exports there are connected to happiness surveys for that country. And you can see that it correlates in a very visually compelling way, where lower scores on all of those vertical bars are in purple and higher scores are in yellow based on the final column of happiness. But of course, in reality, the kind of hyperparameter interaction plots you make are not going to look this clean, so what can we do? A good general strategy is to start with whatever simple architecture already exists in the code you're looking at, or the state of the art for the problem that you're solving. And after manually testing a few runs to set the epoch and the data set sizes, like I talked about, maybe some other hyperparameters that you want to keep fixed, you have the setup for a nice exploratory sweep. And for that, I would suggest a small set of hyperparameters, like 3 to 10. The more you start with, the longer this iteration is going to be. For each hyperparameter, sample a few values in a wide range. And even if these fail, you will have a better sense of the search space. For example, I would try several orders of magnitude for learning rate, 0.01, 0.001, 0.00001, and so on. At the same time, I wouldn't get into very fancy values at this point, and common defaults do pretty well. I find that exploring the training dynamics, how slow or fast your network learns, is really good in a first pass because you can get easy wins here by falling in the right range. With a learning rate, like I talked about, you can get most of the information about how sensitive your network is to that hyperparameter by sampling just a few values. You don't need to know if it's 0.001 or 0.0015 as the best absolute value. I have optimizer here in parentheses as well because it's going to be highly correlated with your learning rate and batch size, but it can have a huge effect on convergence overall. For example, Atom is generally great for many things, but I have seen projects where SGD outperforms it massively. Once you have these things set up, the next candidates go into more advanced details like layer sizes or the number of filters, or perhaps the shape of the filters. The overall network architecture is great to explore here, but I would avoid making too many changes at once. As an example, I would construct 2 or more versions of your architecture that capture the general difference between your ideas. Let's say a regular RNN and a bidirectional RNN, or a CNN with max pooling versus with average pooling, and use those as categorical variables. If one of your hyperparameters is the number of convolutional blocks, then another is the number of filters in each layer, and then another one is whether you're using max or average pooling, you very quickly have a combinatorial explosion, which is exactly what we're trying to avoid by keeping these iterations and these iterative sweeps tight and manageable feedback loops. On this note, dropout can be good to test, but usually after you've already established a pretty good baseline, I find if I increase it too early in my exploration, then a good fraction of my runs just don't learn anything. And then you could throw in other details like weight decay, learning rate schedule. The possibilities are really endless. And my overall advice would be to stick with a simpler sweep than you might want at first and just see what happens. In terms of seeing what happens, I would really recommend, as tempting as it is to track every run and see how you're doing, once you've verified manually that the training loss and validation loss are generally decreasing, and maybe the accuracy, hopefully the accuracy is going up, then just let it run and focus on something else, because that's the whole point of automating this step. You don't need to check in on how experiment A did in order to launch experiment B. You're really letting the automatic hyperparameter tuning work for you. With some tools, it's also easy to scale your sweep by running the same launch command for an agent managing the sweep on multiple GPUs, and those can parallelize your work very effectively across as many GPUs as you can get. Of course, periodic checking is fine too. It's hard not to get excited about your metrics improving, and sometimes you can catch unexpected failure modes earlier. Finally, it's useful to set a limit in advance, such as the total number of experiments you'd like to try, or the amount of compute or time you want to spend, as much for efficiency as for your own sanity. I've wasted a lot of time, more than I'd like to admit, watching sweeps and hoping that they'll hit a magical combination. And really, there's no optimal answer to this. Look at the results and see where they're at. At worst, I try to not go for twice as long as the amount of time it took me to get the last best run. And now that you're looking at the results, it's really helpful to write down your plan and analysis explicitly. That way, it's easier to be intentional about the next steps, and also for my future self to understand what the heck I was doing. And from there, you can increase the range of hyperparameters that you're trying of the values. Sometimes you can increase the precision if you'd like to find a better value between, say, 0.01 and 0.001 for learning rate. Add new hyperparameters, and of course, convert some variables to constants to expand the search space of your sweep. In some tools, you can also mark some of your best runs from one sweep to make sure that they're counted as points you've already visited in your future sweeps. And there's lots of ways to run this analysis. One thing you really want to look for is, as I showed with that parallel coordinates plot, how different hyperparameters correlate with your result metric. And so now I'll hop through some concrete examples, and I'll be using visuals from Weights and Biases, but again, there's different tools you can use for this. So this is an example from a convolutional neural network that's using satellite images to predict one of 4 levels of drought or forage quality at that location. So if the forage quality is 0, then it's drought, it's desert. If it's 3, then it means there's lots of greenery for farm animals to eat. And this is an actual community benchmark with open data and open code that we're running on Weights and Biases that I'm really excited about. And here's just an example of an exploratory sweep that I ran on this. I used Bayesian optimization to maximize validation accuracy and tried a bunch of different values for the different 3 convolutional layers and then 2 fully connected layers, and some values for the learning rate, which you can hopefully see. It's kind of small in the bottom here. But the general idea is I only run 50 of them, and it's a quick exploration on a tiny slice of the data. And then I can explore correlations by plotting each line, connecting my output metric, which is validation accuracy, with the different values for hyperparameters. And hopefully I can see, this run here with the lowest validation accuracy, those values seem to have been poor choices, whereas all of the better runs are concentrated here. And in some tools, you can explore that interactively. And also some tools offer a parameter importance panel. This is actually just a random forest that's run on top of all of my hyperparameter exploration results. And this sees a strong correlation between dropout and accuracy and the size of the first fully connected layer, which kind of makes sense. The larger that layer, the more representational power we have, and so on. You can also see how different runs in the sweep performed over time. This line connects the best performing runs after a certain point. Here's a different project. In this one, we're looking at PDFs of receipts for television ads that have been OCR'd, and we're trying to detect find from the OCR'd string what the name of the organization is that paid for the ad. And here are just 2 examples. As a human, this is very easy to read, the way we read receipts from a grocery store. And as a computer, it's very hard, especially if you don't have the geometric information. So for this one, I ran a big sweep over lots of hyperparameters, really trying to get the accuracy of an initial model from about 70% to, I got it to 95 eventually. And very high correlation I found was that the number of distractors was highly correlated with validation accuracy. And to explain distractors, in this case, I'm training with 1 receipt and the correct answer for it. And that's 1 correct label. And a distractor is the receipt paired with an incorrect answer that I randomly take from the other labels. And I thought the training in a balanced way would do pretty well because it generally does in most problems. But from the sweep, I learned that actually increasing the number of distractors per correct label gave me better and better accuracy. The problem here was that generating those distractors in memory actually caused a bunch of my processes to crash. So I wasn't able to keep running that sweep for as long as I liked and seeing those results, because the higher the number of distractors were, the more likely the process was to crash. So this is just a reminder to keep the limits of the engineering part in mind as you write these sweeps. And then briefly, a third example. Here I'm looking at semantic segmentation with street scenes. So for each pixel, I want to identify if it belongs to a car, the road, a pedestrian, and so forth. I ran a long sweep here to increase the intersection over union. And the metric I was trying to maximize was the average intersection over union across classes. And the interesting thing I found was that across all classes, there's a high correlation with learning rate. I should set it lower, I'm sorry. Some with weight decay. But if I looked specifically at human detection, then an AlexNet model was the most predictive. And on further investigation, the reason that happens is because AlexNet, here's an example at the bottom here, would not focus on the details, but would detect humans in this, and detect all of the classes in this blocky, patchy way that would just be more correct on average, even though it actually failed overall to get the details. It just had more false positive area for humans. And here's the view of the parallel coordinates chart for that. You can kind of see that AlexNet is the encoder here, and the average intersection over union is lower for those runs and higher for ResNet 34. And just to summarize general advice, I know this is a whirlwind tour. It's good to have 1 script that you can run manually for a hyperparameter combination you'd like to try, and 1 that you'd like to sweep over, so then you don't have to maintain 2 separate states of your code. The shorter you can get your experiments and the shorter you can get your sweeps, the tighter your feedback loop and the faster you can move. I would recommend biasing towards exploration first, trying wider ranges in the space, and then focus in later. But don't focus in too much, because change happens very quickly in this space. With that PDF receipt extraction project I showed, a few days after I got my model above 95% accuracy, Google published a paper that uses a very different and much better approach that completely blows all my optimization out of the water. And also don't explore too much at first, because that slows down how fast you can move and make helpful findings happen. And finally, all of these choices are a depth-first tree. So as you make 1 decision and tune 1 hyperparameter, that kind of narrows down the spaces that you can go afterwards. So just be mindful of that. And of course, for all of this, your mileage may vary. Your problem might be very different. This is generalization over training tons and tons of different models in the convolutional recurrent net space. And finally, this visual here is just a reminder about the confidence interval of these types of hyperparameter searches. The top one is picking up on an actual pattern where the hidden size, the higher the hidden size layer in a network, the higher the accuracy. Whereas the bottom one is actually just varying the random seed over the same number of runs. And this is a reminder how patterns can be noisy, and always keep in mind how many versions of your experiment you've run as you try to draw these conclusions. And that's all I have today. Thank you.
Well, Stacy, thank you so much for that. I've collected the questions. And what I'm going to do is, we've got a lot of questions from that Abe guy, which is me. But I'm going to go ahead and put, I'm going to put the other questions first, because I want to be focused on the customer. So the first question is, does the hyperparameter slide with yellow and purple waves include Bayesian hyperparameter tuning?
Yes, so that's the results of runs that have been selected by an agent that uses Bayesian optimization to pick the next ones it tries.
Awesome.
So, yes.
And on the manageable and iterative sweep slide, there was a question, does this approach change when using GBDT, which I'm assuming is gradient boosted decision trees?
Yeah, so I haven't trained many models with that myself. This is all focused on convolutional neural networks and recurrent neural networks with deep learning. So I think you could use the same approach, but honestly, I haven't trained a model like that myself.
Okay. There's a number of questions that are related to the fiber plots. So I have the same question. When I look at those, I just see a bunch of yarn, and I'm trying to understand if you could break down, like, some of them have like a lot of sparse space and thin lines, and some of them like have dense areas, and it's on the left and on the right, and the waves. And what can you go through and explain some of the charts in detail, and like what you're looking for, and how you use these things? And then other people are asking, are these plots, where did you get them from? What library? Is this part of weights and biases out of the box? Or?
Yeah, so this is an automatic part of weights and biases. I was framing, because I was asked, this whole talk as a general presentation and not specific to weights and biases, but yes. I use these a lot. I think this might be a good one to look at. So the rightmost column that has the color gradient fixed, that's showing our result metric. This is what we really care about in this model. In this case, it's intersection over union. So that's when we're detecting humans or cars, what fraction of the pixel is overlapping correctly of all the pixels, right? So the higher it is, the better our model. So then for each sort of result on this rightmost number line, the line is drawn to connect the points on the other number lines that correspond to those hyperparameter values for that model. So, for example, when we set the batch size to 8 and the encoder to ResNet 34 and the learning rate to 0.004, we can trace through all these. Then we get an IOU of, say, 0.78. It's hard to.
I'm sorry. When you said that, because I'm here, and I apologize, the screen went a lot smaller, and you can't read any of the values. So when you started describing those things, it was like, I can't read it, I can't see. Can you kind of put the cursor and and go through that again so that we get kind of
here? Let me go. Is it bigger in this one?
Okay, so you can see biocapacity production.
Biocapacity production imports, yeah. So sorry, the numbers are really small, but just trust me that they're increasing from the bottom to the top.
Okay.
Right?
Yes.
And each line is an experiment or model or run. that connects the values for that model or experiment or run across all of the columns on the left, and then the final output result is the column on the right. So in this case, and I'm using a toy example here because I think it illustrates the problem better.
Yeah.
You know, for a given country, it looks like the higher, you know, the exports, generally it goes from purple to yellow as we increase exports, and the happiness also increases. And then if you were looking at a real machine learning experiment, then you could see, oh, as the learning rate increases, the validation accuracy also increases.
Oh, okay. So then you're looking for, then what would you say you're looking for when you look at this chart to say, this is a great model. Do I want higher waves and higher, you know,
Yeah. Exactly. So I'm hopping back to one that I know is hard to read, but represents an actual model. So this column here is encoder, and you can see that there's a lot more orange and yellow going to this value here, which is ResNet 34. And there's mostly purple, which is lower scores, going to this value here, which is AlexNet. So if my goal was to pick an encoder that increased my performance, improved my results, then I should probably use ResNet 34 instead of AlexNet.
Okay, now I get it. So you're always trying to pick the yellow and the, well, it's not necessarily the higher, but just, is it the higher, or you want?
So a lot of the time these are numerical values. So for learning rate, it does go from 0.001, 0.002. But the example I just showed, you can also log categorical values, or sometimes you might be in a world where the scale is flipped for some reason, right? You actually want to minimize the cost, let's say.
Okay. Okay, very nice.
Yeah.
The next question I have is, do you suggest a particular way of logging all of the hyperparameter results, or at least the most promising ones? For example, keep an Excel spreadsheet with best params and the metric.
Yeah, so that's a great question. That's what I used to do before I started working at Weights and Biases. This is a tool that logs them for you automatically and keeps stuff organized. Yeah.
Really, so it keeps track of all the hyperparameters and everything you tried, and you can, and it's all there. It's in the graph, so it has to be somewhere, and you can, and it should be able to tell you kind of, right? Make predictions and say, or not predictions, it's just say, this one's probably the best model, right?
Yeah, so, and that's, you can either sort them yourself by, by the results that you're logging, or then this parameter importance panel, which is, as I said, just running a random forest model on top of your results. So you could, you could put your hyperparameters and results in an Excel spreadsheet and then train a random forest on it yourself. You would get hopefully matching results that say, hey, learning rate is the most impactful hyperparameter that you valued. And here, for example, it's negatively correlated in red, which means you should try to set it lower and then you'll get better results.
Very cool. Okay. And then the next question is, how are the importances measured? Is it dependent on the type of search algorithm you choose?
So that's a great question too. The order of the experiments and the values that you try are determined by the method that you choose. So if you're choosing random, then each new experiment has randomly generated values for the hyperparameters. But then you can run this parameter importance panel on that data regardless of how you gathered that data. It's just that if you explore them randomly, or say if you use grid, right, then you're trying every possible combination, then it might take you a longer time to get to the best possible combinations, which is the whole point of something like Bayesian search, Bayesian optimization, that will help you pick those best combinations faster. So that's why I generally recommend that one, because it will, in practice and in theory, lead you to those faster.
Okay. And there's some other, so I think this one was kind of answered, in terms of how do you compare results of one hyperparameter to another, but I think that's here, right? Or
so this is here for two different goals, and on the left, I'm maximizing my accuracy, or sorry, my intersection over union on humans, and on the right, on all of the 20 different classes on average. I think what this question might be getting at is, how, if I have 10 different hyperparameters, right, how can I really disentangle the effects of, the first one versus the other 9?
Yes, that's right.
And the answer is, if you really want confidence bounds on that, then you'd have to rerun, a number of experiments where that is the only thing that's changing. And the closest I have to that is on that last slide where I show these two comparisons. So the bottom is 210 versions of the same code with a different random seed, like literally all of the hyperparameters are the same. And here, they're all conditioned, so there's 210 divided by 3 or whatever. So 70 runs with different hidden sizes, 70 runs with different batch sizes, and everything else fixed. So that's a way where you can say, like, I ran with these, with this specific hyperparameter configuration, say 10 or 20 or 50 times, and that gives me a bound for the average accuracy. And then you could compare it to the accuracy bounds for when you ran, 10 or 20 or 50 times with a different random seed, let's say.
Okay, very nice, very nice. The next question, and please let me know when we're pushing against your time limits, because there's a lot of questions here. So, you've done a great job, Stacy, and there's a lot of interest. So the next question is, what is the go-to hyperparameter tuning model to use first?
Yeah, so I was trying to make a case for that being some form of model-based optimization in this talk, because we know that that's generally going to do better. The only reason not to do that is if you don't know what your objective is. So if you aren't calculating accuracy yet for some reason, or that's like very hard to compute, even then you might be able to use validation loss ideally. But yeah, I would recommend some sort of optimization if you're going to do this anyways. But yeah, then there's like all sorts of debate about particular algorithms or details, and I'm sure someone could come up with a model that's an exception. But yeah, overall, yeah.
Strengths and weaknesses. Yeah. One of the listeners was wondering if you could share your GitHub ID.
Oh, you can. I wonder what the easiest way.
If you put it in the chat, that might be,
Yeah, I can put a link in the chat. I also just prefer to share like on my profile on Weights and Biases, and then you can find my code from there.
Oh, okay. Well, it's up to you.
Yeah, I will do that in a sec. Yeah.
One of the other listeners was asking, do you have any opinions on better Bayesian optimization libraries and the pros and cons for Optuna?
No, I don't. I'm very biased in this space myself. It would, I've looked at just the overall approach, and I think, it depends on what you're used to, but I've been working on this particular way of doing them for quite a while, and I think it balances a lot of what's really useful.
Okay. So Jan has a question here. What is your strategy with random number generators? Are you using the same set of hyperparameters with different random seeds, or keeping the random seed at one value for all of the different hyperparameter tuning values?
Yeah, so if I do set a value, I keep it to 1. In generating these, I believe that for the random one, there's actually just no random seed set. So it's the inherent randomness.
Right, right. Okay, and then we have another listener. Alex, is there a library for plotting these cool orange and purple diagrams? So outside of weights and biases, is there some third-party open source library that can do the same thing?
So weights and biases is free to use for open source projects, and the code is actually open source. It's a Python package. The part that's not open source is the visualizations and the front end of the browser. This is a type of plot that I've seen in other environments. It's not a type of plot that we've invented. So I think any graphing library that has multiple axes and coordinates like this should be able to do it.
Okay. So I've still got a number of questions here. Are you still sure? Okay, because you got a lot of good knowledge here to share. So I think a lot of listeners are very, very appreciative of this. So Fan has a question. How do you tell if a hyperparameter should be tuned at each step? And also, how much do you tune? A linear scale or a logarithmic scale?
Yeah, that's a great question. So how to tell if a hyperparameter should be tuned? I mean, usually I'm starting with, the model needs to be improved, and I am, if I'm starting from scratch, then I have like my own intuitions, which I try to address in the these are the ones you should tune first, these are the ones you should think about next section. If I'm looking at someone else's code, I try to see, start with the values they've arrived at, and especially if they have any comments or, paper on sort of what they've explored, then definitely use that. Otherwise, again, like the training dynamics ones are easy to tune because we sort of know how they work. And then getting into the architecture, there's some general intuitions, right? Like you could increase the amount of representation, have bigger layers, more layers, but then balance that with not overfitting. So it's sort of an iterative practice like that. In terms of how much to tune, that gets at this notion of iterative sweeps and the slot machine in terms of knowing when to stop, because you could just keep trying different combinations, right? Even if you've tried 0.01 and 0.02, you could try 0.015, and then you could try 0.0125, and so forth. So I would look at how much gain I'm getting out of that process. And, if I've run a sweep, if I've run several series of sweeps, and on the last one, I'm getting into the second or third digit after the decimal, then it's sort of diminishing returns, right? I guess the final important note here is it depends on what your goal is, right? I often think of the explore-exploit as are you trying to understand what matters to your model, what different general insights you can get about the architecture, or do you really need to deploy this, and that 0.001% is going to be a difference of thousands of images that you misclassify? And the answer would depend on that.
Okay. There's another question here. What if we have a large training data set split to train and dev from general domain data, and then several test sets from a few specific domains of the problem? How would you do hyperparameter tuning in that case?
Yeah, so I would think about the accuracy on each of those sets as a separate metric, and I realized that I would train a model, train one model with one set of hyperparameters, and then validate it on those 3 or however many separate data sets. And then, it would be most similar to that case I showed with human IOU versus general IOU. You'd have to do some sort of balance like that. You could also, if you have some relative importance on those metrics, you could like try to average them out into a single metric. Most of what I presented, and this is kind of why I left out GANs and reinforcement learning as well, is Bayesian optimization works looking at one parameter, and you have to get a little bit clever to, sorry, not one parameter, but like one output result metric. If you have multiple ones of those, then you have to get clever as to how to represent it as one, or maybe try to have a separate pass where you look at which direction each of your 3 or more metrics are going and try to synthesize across that.
And there's the final question, Stacy. Thank you so much for being a trooper.
Of course.
Karthik was saying, thanks for the interesting talk. Can you share some resources about Bayesian optimization? He wants to know what you think about, what are good resources for learning Bayesian.
Good resources. I would literally type that into Google Scholar and look at the papers. I know there's a hyperband paper that's pretty famous that I think focuses more in the early stopping. And my caveat here is also just that I haven't gone super deep on the different theoretical comparisons and research. But I know that this is a whole field and it exists.
Awesome. Well, thank you so much, Stacy, for your time today and your great presentation. Thank you, audience, for being here, asking great questions. So with that, just gonna, let everybody give a little bit of applause for Stacy. Thank you. I'm gonna go ahead and we're gonna end it there. Thank you very much, Stacy.
Great. Thank you so much.
All right.